Thank you very much for inviting me and giving me an opportunity to talk about my work. And so this is not about integrability, neither integrability nor TT-bar deformation. And so it's in the category of this duality and related topics. And so my talk is going to be based on the work in collaboration with Oren Bergman. Okay, so here's an overview. So by the way, it's not 34 pages, it's about 20 pages. And so I hope I can get to the end. And if not, I will stop somewhere. Okay, so here's an overview of my talk. And so it is about the most well-known ADS-CFT, that is the duality between n equal to 4 SU and super mills, and type 2B superstring theory on ADS5 plus S5. And as you know very well, here's the correspondence. You have gauge invariant local operators in the field theory, which is dual to massless and massive string excitation modes. And the field theory also has non-local operators, such as Wilson loops and Toft loops. And they are dual to branes. And in the case of Wilson and Toft loops, they are dual to a fundamental string and D strings. And in addition, we have correspondence between the generating function of correlators of the field theory, and that is dual to boundary deformed partition function of quantum gravity via GKP Witten dictionary. So this is a well-known story. And so today, what I'm going to do is to discuss some fine prints in this duality. That is, so instead of having SUN group, I talk about SUN algebra, then you will see that there are not a single n equal to 4 SUN super mills, but you have a class of SUN super mill theories. So I put the emphasis on this plural S. And so these different SUN theories are distinguished by one-form symmetries and its associated line operator spectrum. And in the holographic dual, so these differences are encoded in the possible boundary conditions on the two-form fields, Nouveau-Schwarz and Ramon two-form fields. So my talk will really focus on non-local operators in the field theory. Therefore, on the gravity side, I will focus on the branes. And for the most part, I will focus on the fundamental string and D string. And that, so it's a Wilson loop and Toft loops. And if I have time, I want to also talk about a generalization of ADS5 CFT4. That is, it's a generalization to SO and SP algebras. And in which case, S5 of ADS5 plus S5 is replaced by RP5. And in this case too, we have class of different theories, and they are distinguished by different one-form symmetries and its associated line operator spectrum. But also in some cases, we do have zero-form symmetry and the corresponding local point-like operator. And the holographic story is very similar to SUN case. And so these differences can be encoded in the boundary conditions on the two-form fields. But there's some difference from SUN case. And so in fact, line operators are not just dual to fundamental and D strings, but also there exists 5 branes wrapped on RP4 in RP5, because RP4 is a non-trivial cycle. So this is the overview of my talk. And here's the motivation. So recently, non-local operators and higher form symmetries, so under which they are charged, gained renewed interest in quantum field theory. So, and there's a new type of symmetry structure a higher group with invariable symmetry generator or higher category with non-invariable symmetry generators. And so there are new insights into the phase structure of QFT by studying this higher form symmetry. That is from the mixed Toft anomaly involving higher form symmetries. And also higher form symmetries can be used to reveal the intricate structure of the duality web, which I will address in this talk. And so this was the field theory development. And then meanwhile, string theory naturally hosts the ingredients for all these ideas. Non-local operators, we know very well that string theory has a variety of branes. And higher form symmetry, if there is higher form symmetry, you have corresponding gauge fields. And string theory naturally have these higher form gauge fields, Ramon and Nouveau-Schwarz forms. And higher group or higher category, this is in string theory, they are described by a combination of branes or bound state of branes. And so via ADS-CFT, so we can expect to gain a more elementary and intuitive understanding of the recent developments in higher form symmetries. And so I hope that this line of study provides new perspectives on QFT and string theory. So this is the motivation. Okay, so first I introduce different SUN superamide theories. So this is what I mean by different SUN superamide theories. So the key is to gauge the center symmetry of SUN group. So the SUN group has the N center symmetry, and you can gauge a subgroup of Zn. So for example, if you gauge ZK subgroup of Zn, you get N equal to 4 SUN mod ZK superamide theories. And in my talk, you will see this K prime, and K prime is defined by this relation. So the N is a product of K and K prime. So therefore K prime is N over K. And indeed, in fact, you know one of these theories very well. For example, the S dual of SUN theory is, to be precise, the gauge group is SUN mod Zn. So the magnetic theory of the SUN is actually one of these theories. But this is not the end of the story, and the life is a little bit more complicated. So the SUN ZK theory are further classified into sub-theories distinguished by the line operator spectrum. So we have a given SUN mod ZK theory, but that's not enough to specify the theory. So we have to discuss which line operators are allowed. So, and to be more specific, this is what I mean. So this is line operator spectrum. So this is the notation for the line operator spectrum labeled by K, I introduced in the previous slide, and in addition by L. And so ZE and ZM, ZE corresponds to the Wilson line, and ZM corresponds to the Toft line. And so in this notation, E and M, they are integers. And so this is actually the lattice of line operator spectrum. And so for example, this K comma 0 means that you have K Wilson lines. And L comma K prime means that it's a bound state of K prime Toft lines and L Wilson lines. And from the field theory viewpoint, these can be found by imposing the mutual locality condition, or so this is the Dirac charge quantization condition. So that's how you can find all the possible line operator spectrum. And there's an additional label L. So therefore, the different SUN supermembrane theories is denoted by this. So SUN mod ZK, and in addition, you have the label L. And L runs from 0 to K minus 1. It's related to the mod ZK periodicity. Okay, so here's the different SUN supermembrane theories. And I now go to one-form symmetry, or I discuss a little bit more about the details of the line operators. So first, let me consider the most basic SUN theory. And I claim that it has a ZN electric ZN one-form symmetry. So what I mean by this is that Wilson loop transforms under the center ZN symmetry this way. So it's charged under ZN, and it has the ZN charge. And so the Wilson loop couples to one form, and that's the one form symmetry. I will elaborate on it in a minute. And then if we go to SUN mod ZK theories, the electric symmetry is ZK prime. And the reason is that because we gauge ZK, and so the Wilson loops has to appear in K groups, the group of K Wilson lines to be ZK invariant. And so then the charge of this K of Wilson line is actually e to the 2 pi I over K prime, and implying that this has ZK prime one form symmetry. And that's not the end of the story for this. And so, for example, if I take the simplest SUN mod ZK theory, that is when this L is 0, then the full one form symmetry is ZK prime times ZK. So ZK prime is the electric one form symmetry, and ZK is the magnetic one form symmetry. The reason is that there is, so in addition to this Wilson line, so in the LK0 case, you have K comma 0 and 0 K prime, and therefore you have K Wilson lines and the K prime Toft lines. And this K prime Toft lines has the ZK charge. So that's why you have ZK prime times ZK one form symmetry in this case. And the most general case is a little bit complicated. So it's SUN mod ZK L theory. So at the end of the day, we can show that so this theory has this one form symmetry. So this ZCD is the greatest common divisor, and we have a few parameters, K and K prime and L. And so the one form symmetry depends on the greatest common divisor of all these parameters. And so to explain a little bit more, so according to this spectrum, we have this Wilson line and this Dionic line. And if you look at these carefully, then you will realize that this has well, as I explained, actually there's a ZK prime periodicity, and this one actually has this periodicity Zn mod ZCD K prime L. But these two are not completely independent, and there's an operator relation, and this relation has another periodicity, and so you have to divide this by this. But then by massaging Wilson lines, the Toft lines, and then you can find a very convenient basis, which is the diagonal basis with respect to this product one-form symmetries. So this is the specification of the different SUN mod ZK theories, and I will move on to describe this in the type 2B superstring theory. So maybe if you have questions.
Sorry, can I just ask one naive question? So all of these Wilson lines that you're writing, I would have thought that the charge under the one-form global symmetry depends on which representation you're taking. Are these all in the fundamental, for instance?
Well, so the Toft lines, well, I mean, it's a finite group, Zn, and so there's only one type of representation.
No, I mean, which representation of the SUN, right? There's one Wilson line for each rep of the SUN, right?
It's fundamental, yes. So yeah, so I'm focusing on the most basic one. So it's a fundamental Wilson lines and Toft lines in fundamental representation.
Okay, very good. Thank you.
Okay, so the holographic description is actually rather simple. So we have type 2B supergravity action, and then as is well known, we have Chern-Simons term. This is the B wedge DC wedge F5. And on ADS5 plus S5, we have n units of 5-form flux, and therefore we get a 5-dimensional action of this type, the BF type. And so this is a topological action. And all the differences in this SUN mod ZK L theories is encoded in this action. So Witten discussed this in the case of SUN and I think SUN mod ZN. And the one-form symmetry is it corresponds to in the language of string theory, the one-form symmetry corresponds to the one-form gauge parameter of these two forms. That is on the boundary, and that is global. So on the boundary, we have global one-form symmetries, but in the bulk, we have gauge symmetry. And what we're gonna do is, so this is the topological field theory that encodes all the information about the difference of different SUN mod ZK L theories. And we will quantize this. So we formed a canonical quantization of this topological theory. And then what you find is that the B and C are canonically conjugate to each other. So they are like X and P. And here's the computation relation because you have N. So that your H bar is like 1 over N. And so that's here appears. And I introduced the notation that, so this B and C are the holonomy of two-form fields. That is, so that's the integral of B2 over some two surface, S is little b. And the integral of C2 over some other two surface S prime is the little c. And when they intersect, you have these non-trivial commutation relations. So that's the consequence of the canonical quantization. Right. So now, because ADS5 has the boundary, and so we have to specify the boundary conditions on this B and C. And we can classify all the possible boundary conditions, and that corresponds to all the SUN mod ZK L theories. So the boundary condition for the simplest case, SUN, is given by this. So it's a little bit, it might be a little bit confusing. What it means by this B equals 0 is that we don't have so here it means that the components of B field, which is tangent to the boundary, is vanishing. So that's what it means by this B equal to 0. And but that does not exclude the B field, which has one leg in the radial direction of ADS, and one leg in the direction tangent to the boundary. So this boundary condition means that we have this B field, and because string couples to this B field, and so it means that this fundamental string, which ends on the boundary, exists. So that's what it means by this boundary condition. And this corresponds to the Wilson line, because the end point of this string is a line. So this is the line operator. And on the other hand, so this is X. So if you fix X, then the P has to fluctuate. And so that's why I say C is free. And so what this means is that you have fluctuating. So now the fluctuating, the components of C2 along the boundary is not vanishing. So therefore you can have surface operator. So there's a D1 brane. But also you can have this component. You can have this mixed component. And so, but this D1 brane ending on the boundary has to be connected to this surface. And sometimes this is called the non-genuine line operator. So the line operator spectrum in this case is just the Wilson lines, and you don't have Toft lines, but you have this surface operator, D1 brane, or to be more precise, this is the D3 brane with magnetic flux on it, discussed by Gukov and Witten. And the third figure is showing the periodicity of the Wilson line. So if you put n of them together, it has to become the identity operator. And there's a brane realization of this mechanism. That is, when you have n fundamental strings, they can end on the D5 brane. And the D5 brane of interest here is the D5 brane wrapping S5. So this is the baryon Barex operator found by Witten long time ago. But except that, so this is now extending in this radial direction. So in the case of baryon Barex, it's extending along the boundary. So it's a kind of cousin of the baryon Barex operator. But when you have n strings, it can end on it, and it's screened. So that's what it means by this n of Wilson line becomes identity operator. Right, and so this is the simplest case. And S dual of this is C equal to 0 and B equal to 3, which corresponds to this SUN mod Z n theory. Right. Yes. Okay. And okay. So here's the general case. I try to explain. So the general case is classified by all the possible boundary conditions. And so this here, I'm writing two Dirichlet boundary conditions. And then I claim that all the possible boundary conditions has to be given by these boundary conditions, and they are mutually commuting. And the mutual commutation relation is given by this condition, which is equivalent to the Dirac's charge quantization condition. And the task is to solve this equation, and it can be solved in this way. And in the end, by using SL2Z rotations, and then you can show that, so this condition boils down to this, and corresponding to the boundary condition of this type. So this means KB equal to 0 means that you have to have K fundamental strings, and K prime C plus LB means that you have L fundamental strings and the K prime D strings. So that's the line operator spectrum I introduced before. And in the case of K is equal to 1, K and L equal to 0, you have this N. And so this boundary condition is equivalently described by B equal to 0 and the Dirichlet boundary condition on N times C. Okay, and so here's the cartoon for the line operators. So this is a generic case. So this is SUN mod ZK and L. And roughly, if you have Dirichlet boundary condition, that means that you have line operator. And if you have Neumann type boundary condition, you have surface operators. And here's the K fundamental strings. And then in this case, you have actually also a surface operator for the fundamental string, as long as the number of strings is 1 to K minus 1. And there's a dionic string because you have this boundary condition, which is a bit complicated, but you have this dionic string ending on the boundary. And also, I didn't draw, but there's a similar surface operator for this one. And all this is about the periodicity of the line operators. So if you put the K prime of them together, it has to be identity. And so this is the mechanism to realize this in the string theory is that you have 5 range and on which these strings are ending. And there's a similar mechanism for this dionic case. And I mentioned some operator relation between 2 types of line operators, and that's realized in this way. So they can be all realized by some brain configurations. I have 10 minutes. Okay, so and then so this is how we can holographically realize all these different theories. So now I try to move on. I'm now moving on to discuss the properties of these theories. Okay. So first, I want to discuss, because in the title, I have duality. And so I first discuss SL2Z duality orbits. Yes, so N equal for SUN superembedded theories, there's SL2Z duality, as is well known. But if you look at it more carefully, it's a bit complicated. So not all the theories are connected by SL2Z transformations. So the structure of this duality web is more like archipelago, and you have islands of duality orbits, but they are disconnected. And so the reason for this is that so there
Is this traffic? Shinji?
this quantity is
Okay. Shinji, connection is a little bit Your screen and voice is frozen.
Sorry. Am I back?
Yes.
Okay, I'm back. Sorry, the internet.
Like,
Okay,
yeah. For 1 minute, we couldn't hear your voice. So.
Sorry, say it again.
So, like for a minute, like 1 minute, we could not hear your voice. So you can start from the maybe in the middle, like you explain the like this SL2. Yeah.
Okay. Oh, okay. Yes. So these different theories are classified by so one form symmetry, and which involves this quantity, the greatest common divisor, and we can show that this is SL2Z invariant. And so if you have different ZCD, then these theories with different ZCD cannot be connected by SL2Z duality because it's a SL2Z invariant. So that's why the web of SL2Z splits into islands and forming archipelago. And yeah, for example, the well-known SUN is connected to SUN mod ZN by S duality in this way. But so then you can apply a bunch of SL2Z and it forms one island, but you can never go to the other ones. And in the end, you can show that so that you can even count the number of these islands or number of these SL2Z orbits. It can be given by a number of square divisors of n. So the n can be, so n is, so you factorize n into integers. And then, so this number of square divisors means that you have some integers which appears at least twice. So you count the number of these integers which appear at least twice in this factorization of n. So that will give you the number of these SL2Z orbits of SL2 of SUN superembedded theories. Okay, and then I mentioned the mixed Toft anomaly of these theories, and there are two types of mixed anomalies in these theories. One is the mixed anomalies in the one-form symmetries when we try to gauge both one-form symmetries, or if or in the presence of background two-form gauge fields. And the other mixed Toft anomaly is the mixed anomaly between electric ZK prime one-form symmetry and the shift of theta. And both of them is encoded in the same Chern-Simons action in the type 2B supergravity. And so here, so the first Toft anomaly is encoded in this form, and the second Toft anomaly is encoded in this expression of the Chern-Simons term. So here, you might be familiar with the fact that there's a C tilde in type 2B supergravity, which naturally appears in the kinetic term for the 3 form. And so this is C naught H3. And if you write it in the F3 tilde, which is more natural, then you get this additional term. And so this will describe the second Toft anomaly. I think with a lack of time, I don't go through much of it. But for example, the second, so this is the second Toft anomaly, and which is given by the five-dimensional invertible field theory. And so this is on the four manifold. it's like it's just theta and B wedge B. So this is the form of a mixed of anomaly for this one. Okay, I don't have, okay, I can, sorry. I will be very quick now. Right, so here I gave a holographic description of anomalies. And I can discuss interface, but I guess I have to skip this with a lack of time. And then I guess in 5 minutes, I will discuss SO and SP case. So the difference of these SO and SP case from SUN is the presence of the orientable 3-plane. And there are 4 varieties, but I will not go into the details of this. And then, as you know, S5 is replaced by RP5 or S5 mod Z2. And correspondingly, you have only half of the flux comparing to SUN case. And in these cases, Wilson and Toft lines are not only in the fundamental representation, but also there appear the Wilson and Toft lines in the spinor representations. For the fundamental one, the description in holography is a fundamental string and D string. But the spinor ones are described by D5 branes or 5 branes, NS5 branes on wrapped on RP4. And the topological field theory that encodes all these different theories is first, this Chan-Simons term. But also to describe these 5 branes, we have to include the kinetic terms for B2 and C2. And here's so you have the Hodge dual of B2 and Hodge dual of C2. And what I denote by tilde is the integral of these 6 forms over RP4. And then you can canonically quantize this, and then you get all the classifications of the boundary conditions, and that's how we can cover all the different SO and SP theories. And here's an example. So I focus on this SO4K, which is particularly simple and it has structures. So SO4K theory has theories are given by this. So you have this spin group and SO, and also you have the label for this L. But I guess the take-home message is so there are 2 kinds of spinors in this theory: S spinor and the C spinor. And the spinor Wilson line is described by this D5 brane wrapped on RP4. And the vector 1 is the same as SUN case, and it's a fundamental string. And then the other kind of spinor is described by the bound state of D5 and fundamental string. And the one-form symmetry in this case is Z2 cross Z2. And if you put 2 of them together, for example, RP4, so that if you put 2 D5 branes together, it disappears. So that's what it means by Z2. Okay. Okay, I'll finish in 3 minutes. And so this SO and SP case, they are a little bit more interesting than SUN case because it has more structures. So I mentioned that SO4K case, you have Z2 cross Z2 one-form symmetry. But some of these theories have, in addition to one-form symmetry, a zero-form symmetry that exchanges S and C spinors. So there's a Z2 zero-form symmetry. And so this part I didn't discuss much, but it's encoded in another topological field theory coming from the kinetic term for 5 form and described by 1 form and 3 form. And this is in correspondence with the fact that in these theories, you have what is called Puffian D3 brane particle, which is the D3 brane lapping RP3. And there's D3 brane lapping RP1 as well. And so this one form is corresponding to this, and 3 form corresponds to this. And then you can consider the fusion of these 0 form generator and 1 form generator. And I kind of skipped the explanation, but so these are given by, so the generators are given by also branes. So in the case of 1 form, it's given by the surface operator I discussed. And for the 0 form symmetry generator, it's described by this domain wall D3 brane. And the generator is described by the partition function of these branes. And then if you make the fusion of them, then, for example, this 0 form symmetry is non-invariable. So if you put 2 of them together, it's Z2, and so naively it's just 1, but it gets additional term. This is a non-invertible symmetry. And the action of Z2 can be understood in terms of Hanani-Witten effect, right? For example. Okay, no, I skipped this discussion, and I think I will finish here.
Questions or comments? Hi, Shinji.
Hi, Minkyu.
So if we study not super Youngkin, but other theory in 4D or 3D, then can you also make this kind of classification by using line equation?
When we consider other theories, which other theories?
For example, Chern-Simon theory.
ABJM. Yes. Well, I didn't discuss. So here I didn't consider ABJM or ABJ theories, but Oren he actually discussed the holographic description of different types of ABJM theories, which comes from the subtlety of this center symmetry. Well, but so people haven't discussed non-invariable symmetry in ABJ or ABJM. So I think the study of this higher category or non-invariable symmetry in holography has just started. For example, these people studied this a couple of months ago. And then there was a paper by Benini and the collaborators. And so it's just the beginning of this study. But it's pretty, I think it's pretty clear that so this appearance of non-invariable symmetry is ubiquitous. So I didn't explain, but the reason why this non-invariable symmetry appears is the fact that, so I mentioned that now in these ideas, now the branes actually become a generator for the higher form symmetries. And then partition function becomes the generator. And then you have the gauge field on the branes. And then you integrate over the gauge field. And then sometimes you have topologically distinct configurations for the gauge field on the brane. And then whenever we have topologically distinct sectors in the brane, that will give you non-invertibility of higher form symmetries. So I think that's the mechanism. And so there will be a lot of examples of this, but people have barely started studying this in the context of ADS-CFT. Was that your question?
Oh, yeah, that's,
I have one simple question. So this SUN superfamily theory is conformal.
Yes.
If you mod up by ZK, is still conformal symmetry maintained?
Yes.
So it has been proven.
Yes, it has been proven, but I mean, well, the gauging subgroup of ZN doesn't affect really the conformal symmetry.
Okay, so in that case, then there are all these operators, like composite operators,
Yes.
which should be forming representation of this conformal group in
Yes. But this gauging doesn't affect the local operators, so it only affects these non-local operators.
Really? So it does not.
Yes. Yeah, because yes, right. So the local operators, they are not charged under center symmetry. So they are neutral under this ZN symmetry, and so the center symmetry doesn't matter for these local operators.
But what is this string theory side? Is that then in superfamily we know now what is the relationship between two objects, string state and this generic non-BPS operators of
Yes.
superfamily.
So for the integrability people with all these local operators, my story doesn't matter. It doesn't change the integrability of large N spin chain. But sometimes you also discuss a Wilson loop, and you put the local operator on the Wilson lines.
That's
That
right.
will be affected.
Okay. So it means non-BPS Wilson loop, you mean?
Yes.
Okay. So how does it change? Because that also has been understood in the context of integrability.
Yeah.
Cost of it. Right.
So I think what will change is only, I mean, people don't care about which lines are allowed. Like you discuss Wilson lines, Toft lines, or Dionic lines. But here, what I'm saying is to be precise. For example, if you are really considering SUN group, then the only line operators you can have is the Wilson line. And then, for example, if you consider the other ones, then for a single Wilson line is not allowed. And so you have to put the K of them together. So I think so most of the people, when they discuss Wilson lines or Toft lines, they really don't specify which SUN theories they are exactly talking about. So I think so that integrability story will not be changed by this. It's just you have. It is telling you that if you want to be precise, then you have to be careful which lines are actually allowed in the theory to begin with. So my guess is that this will not affect the integrability unless I'm missing some subtle points.
But in the string theory side, you are saying that some target space is also deformed, like S5.
Not really. It's the string theory side. It's ADS5 plus S5.
Yes, still.
Yes, and the only thing is that you have to be careful about the boundary conditions for these two-form fields. And as far as I understand, in the integrability story, you don't really have to care too much about the boundary conditions on the two forms.
It is
Yes, so this is really a fine print in ADS-CFT, and yeah, I don't know what's the significance of it, but from the perspective of higher form symmetries, this subtlety is very important.
Okay, thank you. Other questions? Okay, if not, let's thank Shinji again.